Okay, I've got an electric generator here. The idea is to inject more current into an inductor and then get it out, get the magnetism that's produced, turn it into electric current. So the idea is to use what I've done here to make it simple in a demonstration. You have an electric motor, it's a single phase electric motor, and the start winding and the run winding are used separate to produce a 90-degree phase shift between two currents. So you've got your input, and that's driving a current going through a transformer. There's odd number of turns, so there's more turns on this one, 20% more turns, and on this one there's actually less turns. And what that does, it drives more current. It wants to drive more current through there. For these to be balanced, more current will need to flow through there. So I've set this line up here to allow more current to flow through this one, so they will want to remain balanced. It needs to be between 10 and 20% difference, because there's always a you need some well anyhow, I'll just tell you need about 20%, between 10 and 20%. So what that does, it drives more current through there, because the ampere turns want to be even, but you've got to drive it to make them uneven. And what that does, it creates more current through more turns than this side, so you end up with a magnetic field being produced in the transformer core. Now that's a setup on one phase. Then 90 degrees later, you want to cause more current to flow in this one. And what that will do, you'll have a lot of current flowing in this one around there. If you increase the current through here, that will tend to allow the magnetic field to collapse. And what that will do, it will drive the voltage very high. Now to do that, I've got another transformer here, and it's just so it's at 90 degrees. It's pushing a bit of current through here at a low voltage, just to get a current flowing into this capacitor. And once the magnetic field starts collapsing, this will want to get going through this the load circuit up to 10 amps, and it will freewheel in that circuit. And this side will also be have a resonant or capacitor in it to produce like an AC waveform. So just to recap, anything I've missed here, we're actually injecting a magnetic field into this transformer core with an AC from 230, and then we're taking that magnetism out of there by getting more current to flow in the separate winding in another circuit, in the circuit on the load. And so of course you don't need the electric motor here, but that's just a basic way of setting it up to show how it works. What you need is a quadrature or sine, cosine, 2-output inverter. And of course then they'll have to have a power supply, so you need it one at 50 volts, one at 12 volts, and 90 degrees, one at 6 volts. It could be up to 12 volts. But as you can see, if you can get 10 amps going through 6 volts, that's 60 watts. And if you get, there's 12 watts, so 60 and 12 is 72 watts. And if you can get 10 amps going through 230 volts, that's 2,300 watts. So you've gone from, plus the current in this one, which is probably about, it's less than an amp, it's about half an amp, so you've got 25 watts. So you've got a bit over 100 watts. It should be able to produce 2,300 watts. Now it seems quite ludicrous, but anyhow. So okay, we've got 90 degrees, that's one phase after the other, I1, I2. Then you've got that's the relationship between the input and this other winding, the start winding in the electric motor, going to this other transformer. So that's the relationship of those two. And then you've got the relationship between the difference in currents between the one side and the other. Now you see here, this is quite interesting, because if you draw it like this, with one phase slightly, with just following the other one, you'll see that as the currents get up to maximum, the magnetic field actually changes. It gets to zero and then it actually changes. And then as the voltage increases, there's a very small difference between the currents flowing in each winding, and you get a high magnetic field. It's that magnetic field that puts the brakes on the current. So in other words, the current's really flowing fast, and as that magnetic field increases, it wants to stop the currents flowing. So it's really the rushing currents, like a flow of water. You're putting the brakes on it, and it's like really it's like a pump, what do they call it? A impulse pump, like you have in a stream, and I can't remember what you call it. Anyhow. Okay, so anyhow, it's creating a huge voltage. You can draw it a different way here too. You have a zero line, and these waveforms, IA and IB, are slightly out of phase, and they're crossing over above and below the zero, and that denotes how much magnetism, or how much current's flowing, and how much to produce the magnetism in the core. And it's actually very tiny. It's only like a few watts of power is required. Like, this is actually quite inefficient this way on this, because it's through an inductor. You could actually do this solid state. You don't actually need all this. All this could go, and you could just use a just create a 2 output inverter using the quadrature and sine cosine system. There's two ways of doing it. You could use a processor, of course, but anyhow, I've done another little bit of something here. It's just showing how in the system with like if you've got uneven turns, you have to have more current flowing in this one to neutralize the magnetism in the core. In this one here of okay, you've got more turns, you're taking the current directly through, that's putting magnetism in the core, and the one that's going around here will actually assist there. But there's more turns in there than there, so the magnetism would build up, and then you go to that one where you get more current to flow in there, and it'll actually pull the magnetism down. To my mind, it works a bit like a differential between two swings or pendulums. One's this side, one's that side, and there's a differential there, like in a car, and you need to reach from this side to that side. When you give that one a push, that gets pushed that way, and that gets pushed that way. So they're both. So you're pushing off both sides of the pendulum. So that's sort of how this system here is working. When the currents are going like that, the V is almost equal here, although one current's going the other way. Both currents are going in different directions. The V is across here, the voltage across here, is pretty close to being equal. Yeah, I think that's all there is at this stage.